So we left off here last time in our discussion where we began reading energy diagrams in the last section. And previously, we had compared reactions from the perspective of kinetics, which we know has to do with the rates of reactions, how fast something will progress from a reactant to product. And we also looked at reactions from a thermodynamics perspective, where we know that thermodynamics refers to the equilibrium concentrations of our reactants and products. So this has to do with, like I mentioned, concentrations of products to reactants at equilibrium, and also just in general, the relative stability. And we find our comparison with kinetics based on the activation energy. Whereas when we talk about thermodynamics, we're going to compare delta G values. So let's take a look at this energy diagram here. And we see our reactants, A and B, have two different pathways to convert to products. So we see our products E and F and our products C and D. So from this energy diagram, we can tell that the formation of products C and D would have a lower activation energy. So this is our kinetics comparison here. So when we go from A to B, we have this activation energy, and then we also have this pathway's activation energy. So we can see that the activation energy from A and B to convert to C and D is lower. So they would form faster. So that's the kinetics analysis. And then we can also see here that C and D are at a lower energy overall. So C and D, when we compare our delta G, our change in Gibbs free energy, since they are down here at a lower potential energy, they are also thermodynamically favored, and they're called more stable products. So this is our thermodynamics analysis. So in this scenario, both the kinetically favored products and thermodynamically favored products are the same, C and D. That may not always be the case. So in this example here, we can see that we have, again, our reactants A and B and two sets of potential products. So we have E and F and C and D. So first we can do our activation energy analysis here to compare for rate, or which products would form faster. So the lower activation energy would tell us that products E and F would form faster, and they would be kinetically favored. When we look at the energy overall of our products, the lower potential energy would be with products C and D here. So when we do a thermodynamic analysis, C and D would be our thermodynamically favored products because they are more stable. So again, it's not always the same products that would be kinetically favored versus thermodynamically favored. And you have to compare, again, the activation energy for your kinetics analysis, and then the overall potential energy or the change in Gibbs free energy for your thermodynamic analysis. All right, so let's take a look at our next slide here. And what else can we tell from these energy diagrams? So here we see three different transition states. So these are the maxima, the peaks of our energy diagram curve. And down below where these dots are, we see 2 points of intermediates. So intermediates are after, in this case, the first transition state, we could have this intermediate form, right? So it goes from this high energy state here at the transition state to a lower energy state as an intermediate forms. And this pathway takes us through 3 steps in this mechanism. So we would have, in the end, 3 different transition states, 2 intermediates before we end up getting to our final product. So that's how you could interpret transition states on an energy diagram and intermediates. In this case, we see we're actually going to look what is observable, what is not observable. So the transition state We know it exists at the maxima, at the peak of our energy diagram, but in a laboratory setting, we cannot actually observe the transition state. So we won't see a molecule in this green box here in this form. We won't be able to isolate this or observe this actual state, this transition state. It happens usually very quickly. It's at a highest energy point here on the diagram, so it doesn't last very long. Intermediates, on the other hand, we can talk about isolation of those or actually being able to observe those, but transition states we cannot. So and in this specific case here, we see a bond breaking and bond forming at the same time. And this is the general notation of a transition state. So we'd have our molecule here, our CH3Br, and at the same time, the bromine carbon bond is breaking, we see that our carbon chlorine bond is forming. That's what those dotted lines are showing you. And then we box in brackets, our transition state, and then we put this symbol here, which is referred to as a double dagger, to indicate that we are talking specifically about the transition state. So everyone knows what our drawing represents. So here we see both our transition states at the peaks here, and we also see this minima on our curve before we get to products. And this indicates an intermediate. So these intermediate species form, and they're represented at these energy minimas on the diagram, so the low points. And these are actually observable. So that means that we can isolate an intermediate. They are a species that exist for a certain period of time before they hit the next transition state here and then can progress to products at the end here. So these are our products. So again, transition states are not observable, but intermediates are. So the last concept that we'll discuss is this Hammond postulate. So the Hammond postulate tells us a little bit about what our transition state will look like. And we can also generalize depending on whether or not a reaction is endothermic or exothermic, what our transition state would actually look like. So we see 2 points isolated here on our energy diagram, one at the transition state, and then the second point here as we're going towards products. So we can see that they're very close on our energy diagram, so their structures look very similar. So that's the first step when we look at this Hammond postulate concept. Now we can expand upon this and again, using our knowledge whether a reaction is exothermic or endothermic, we can determine what our transition state would look like based on the energy difference between our reactants and our transition state or our products in our transition state. So in an exothermic reaction, we can see that we have a closer energy from our reactants to our transition state. So if we looked at our molecule at the transition state, it would more closely resemble our reactants. So that's with an exothermic reaction, right? We see that transition state resembles reactants. And then on our second energy diagram, we see that in an endothermic reaction, our transition state would be closer in energy to our products, and therefore the transition state of an endothermic reaction would resemble our product. So that is everything for this tutorial. We will continue with section 6.7 next time and some new terminology when we discuss nucleophiles and electrophiles.